Hi, my name is Madison Rye from Ally PLM. I'm here today to talk to you about Solid Edge Simulation ST5. Ally PLM Solutions is located headquartered in Cincinnati, and we do software and services. We're a reseller for Siemens PLM. You can see the territory we cover. We actually have customers outside of that area as well. Today I'd like to talk to you about analysis steps, and then I'm going to do 3 demos for you, a structural, a modal, and a thermal, and then we're going to talk about results verification. As you know, simulation is kind of the in-between for Simulation Express and FEMAP. So, Simulation Express is for one part for static and modal. FEMAP will do just about anything you want it to do, and the in-between Solid Edge Simulation does statics, modal, buckling, and now thermal analysis, which is new with ST5, which we're going to talk about. In all simulation, you'll have problem description, which is very important, simplification, which is also very important, pre-processing, solving, post-processing, and results verification. And all those steps are critical in any FEA analysis that you're going to do. And this software is really for the design engineer. It's not meant to be used by a full-time analyst who's doing high-end work. That's more a product that FEMAP, you would use FEMAP for. There are many benefits of simulation. The best one is really its ease of use, and I think the other one is that it uses an Astran solver, which is the industry standard in solvers. There are a number of other ones, and we'll talk about that as we go along here. There are a number of new things with ST5. These things are included, but the big thing really is the thermal analysis, and we're going to show you an example today. So why don't I get on to it here? All right. I have the Solid Edge Simulation in ST5. We're adding functionality, which we're going to talk about as we go along here. But I want to show you not only the really cool stuff with ST5 that's new, but also discuss how to use engineering judgment during pre-processing in order to make the correct assumptions, and during post-processing in order to validate our results. So we're going to start with a static demo. This is a Hussmann shelf, refrigerator shelf. Actually, this isn't the actual geometry. I just modeled it up myself after an old Hussmann refrigerator shelf. If you go in Walmart or your local grocery store, you're going to see Hussmann refrigerator units, those big refrigerator freezer units everywhere. So the first thing that I need to do here is determine my physical situation, and this is critical. I see so many times people just throw something in and see what they get. You know, that's not what this tool is meant to do. That's not what any finite element analysis tool is meant to do. You have to be very specific in what you're looking for, and the reason for that is because we make simplifications along the way. So if, for instance, we wanted to look at if these brackets the stress in these brackets is not higher than the yield stress, then we would have to include the geometry where this is hooked into, so that rack that the shelf is hooked into. It's kind of like using zones in Solid Edge, where if you're looking at an area of interest, you want to draw a box around that area and make sure you include everything there, the loading, the constraints, and the geometry just as it is. Now, in this case, we've already done that analysis, and we're looking at a standard that tells us that the deflection at the end of this shelf can't exceed a 1/4 inch under 100 pound force of load. And that's about 6.35 millimeters and 444 newtons. So we're going to round it up to 500 newtons. So the end of the shelf here can't deflect more than about 6 millimeters. So our area of interest is here, and because our area of interest is here, there's a principle that says that we can make simplifications as long as they're not close to our area of interest. So we're going to say that we can simplify by not including this, what this is hooked into, which will greatly reduce our solve time. Now, we've got to think about how this is hooked in. So if you think about it, it's kind of hooked into a receiver there, and these horizontal lines here, they can't move in this direction because it's hooked into the receiver, and same for over here. In addition to that, this shelf sits up against the back of a refrigerator, so you're going to see that these areas can't move in the Y direction. They can't move through the back of the refrigerator shelf, obviously. So those are the constraints we're going to do. So that's how we set up our problem. We have to understand exactly what our situation is, what our problem definition is, which in this case is the deflection here at the end of the shelf, and then what our simplifications are going to be. Now the next thing we need to do is take a look at simplifying the geometry. And the reason for this is because you guys have all seen a mesh. You know what it looks like. It's little triangles or squares all over this thing. The aspect ratio, which is in geometry check, and all that means is it's just a comparison of the length and the width of your element. And the element is just those little things in the mesh you see all over, the little triangles or rectangles. So the length to the width is the aspect ratio, and that should be around 1. You don't want to have a very distorted element or your results won't be good. So in order to get around these small features, those elements are going to have to be very small. Now for solid elements, it's a tetrahedral. It looks like a pyramid, and they have at all the vertices, where those at all the vertices, those are called nodes. Each node can move in x, y, and z. So it's got displacement in x, y, and z. We call those degrees of freedom. So if and then for a surface element, each node, and it looks like a rectangle. In this case, it's a quad 4 if you're familiar with Nastran. And it has degrees of freedom that are, it also includes the rotational degrees of freedom. So it can rotate around the x, rotate around the y, rotate around the z. So if you can imagine if we had to get elements around these small features, we would have to have a very small element, which would drive up the number of elements, driving up the number of nodes, driving up the number of degrees of freedom, driving up our solve time. So that's why we want to simplify here. Solid Edge makes it very easy to do this. And what I'm going to do is I'm just going to use my Simplify tool here. And you'll see in the Pathfinder that Simplify appears, and anything I do from now forward when I'm in Simplify is going to appear there in the Pathfinder. So all I want to do is delete some faces here, and you'll see that those, when I rotate, you can see that those are green highlighted, so those disappear, and you'll see that now down here in the Simplified. And then in addition to that, I want to delete the holes. And I can just fence select all the holes here, and you'll see those are green now, and I can just get rid of those. And it's really as easy as that. Now the other thing I want to do, and I zoom in here, you can see the thickness. This is a sheet metal part. It's a 16 gauge stainless steel, so it's about 1.5 millimeters. And when I was talking about the elements and having a lot of elements, it's the same thing going through the thickness here. If I had to use a tetrahedral element, since they have degrees of freedom that are only translational, meaning that it's only x, y, and z displacement, I don't have the rotational degrees of freedom. If I had to get, if I want to capture the bending, I have to get 2 or 3 through the thickness. And you always hear that rule of thumb. You want to have 2 or 3 tetrahedrals through a thickness of some part. Well, if I had to get 2 or 3 and keep the aspect ratio okay through that thickness there, I'm going to have very tiny elements. I'm going to have a whole lot of elements driving up my solve time, which is exactly why we have the surface element. Surface element is not a 2D element. People always say that because it's represented by a surface, but the reason for that is because you only use 1 through the thickness because it does have the rotational degrees of freedom. So you apply it to a surface, but it extracts the thickness from your part model. From the Solid Edge does that for you. So here I need a mid-surface to apply my surface elements. So I want to use my mid-surface tool. Since I'm in Simplify already, I could do this in the assembly because we have new geometry tools in the assembly. You'll see my mid-surface there. It's just as easy as that. Here I have simulation geometry where I could do the mid-surface here, but since I was already in Simplify, I'm just going to do that there. Now the other thing, I want to go into the bracket here, and I want to do the same thing. I want to get rid of some of those holes so I don't have to have too many elements there. I can just highlight, delete those, and that looks good. And again, I'm going to add my mid-surface just because I'm here, and it's very easy to do while I'm here. And you'll see that in the Pathfinder there. And the last thing I'm going to do is go into my rib, and since I did everything in Simplify, I'm going to do that mid-surface and Simplify as well just to stay consistent here. So now that I have all the simplified parts, I can just go and tell my assembly I want to use those simplified parts. So there's my simplified model. And now, so anytime you have rounds, holes, small features, you want to try to eliminate those as long as they're not a contributing factor in your area of interest. So now that I've done that, I can just decide that I want to show my surfaces that I've created. So I can just turn off the design bodies and turn on the surfaces. And now I'm ready to go. I've got my mid-surfaces all ready for my surface elements. With simulation, it takes you very nicely here through the toolbar. you create a new study and work your way through pre-processing all the way to solving and post-processing right in the ribbon bar. So it's super easy to use, and that's one of my favorite things about it. I'm going to create a new study, and we have the choice of linear static, normal modes, linear buckling, my steady state heat transfer, and then I have linear static combined with heat transfer, linear buckling combined with heat transfer. These are new with ST5, and we're going to get into that in a little bit. So I'm going to choose linear static here, and notice I have my mesh type from tetrahedral surface and mixed in general bodies. Tetrahedral are those pyramid-shaped elements for solid parts, and surface elements are for the thin parts. Anytime you have a thin part compared to your width and your length of your, like I said, you want to make sure you use the surface elements so that you don't have to have 2 or 3 through the thickness. And you can use that simulation geometry tab if you don't have a sheet metal part. You can offset a surface, copy a surface, and offset it to make a mid-surface. And then mixed in general bodies, new with ST5, we do support a non-manifold condition. So let's say you have a turbine and you have the base of the middle of the turbine, which is a solid part, and you have the fins coming off, the blades coming off, and those are surfaces. You can join those now with unified body, even though that's really a surface coming into a solid part, which is a non-manifold body. We can do that now with ST5 simulation. So I'm going to choose my surface elements, but watch my iterative solver here. It turns off automatically for me because Solid Edge is choosing the best solver. You have iterative and direct. The iterative solver, if you remember from your matrices classes, you substitute numbers in and then you see how close you are to your result. And when you get within a certain percentage error that you specify, then you've got your results. With the tetrahedral elements, that solver is very efficient and very accurate. With the surface elements, the direct solver, where you directly solve for the displacements, is more accurate. So you don't have to worry about that. It takes care of it for you. Here's my geometry check. I talked about this a little bit with the aspect ratio. It's going to check those aspect ratios for you, make sure that you're okay there. You stay close to 1 so you don't get any distortion. You can enter Nastran options here. You really don't have to worry about it if you don't know Nastran commands. If you do know Nastran commands, it makes it easy. You can just type those in there if you want to. And then new with ST5 here, we also have generate only surface results. I'm sorry, we have do not process results after solve. And that means that these things that I've selected get processed at the time of my solve. And then if I want to look at these ones that aren't selected after the fact, they'll get processed in the preprocessor when I click on them. So it saves time in my solve. If I know I'm not going to look at these things, why bother solving for them at that time? You can always click on them later and they'll be solved for. So everything looks good here. Now I just go right into my geometry selection. Solid Edge does that for me very nicely. And I can just fence select everything. And now I can apply my force. New with ST5, we do have everything separated here, so structural loads are separated from body loads and thermal loads. And notice, because I'm not doing thermal analysis, these loads are grayed out there for me. So I can very easily here select where I want my force. I can just flip it, and I'm going to type in my 500 newtons here. And then let's say I like to look at, I'm going to make this bigger so we can see it. And then I only like to have one force. Some people like to see it because it's applied over the whole surface, but some people like to see, the little arrows everywhere. I just like to see one because I got one force. Cleans things up a little. It's whatever you feel like doing. So now that I've applied my loads, I can move right on to my next step, and you can see how easy it is just to follow the ribbon bar into my constraints. So we talked about what we needed to do, and I love this user-defined constraint because I love to be in control of everything. I want to control exactly what degrees of freedom I constrain. And so with the user-defined, I can do that. So I'm going to pick the surfaces we talked about that are constrained in the Z direction here. And you'll notice I get this nice little triad. And you'll see with surface elements I have 6 degrees of freedom here. I have the rotational degrees of freedom, and then I have the Z, Y, X translational degrees of freedom. So all I have to do is click on that Z, and you'll see that it's gone from all my triads now. And what do you know? That's as easy as that. And I'm going to do that again. And I'm going to select these 2 surfaces here that are constrained in the Y, and it's just as easy as that to make them constrained in the Y. So that means that those nodes that are on this surface here are not going to move in the y direction. Their displacement in y is going to be equal to 0. Similarly, these are going to be, their displacement in the z is going to be equal to 0. Now, to make the solver happy, what I need to do is constrain in my last direction. And since I'm not loaded in this direction, it's really not going to matter. Move the triad off here so I can see it. But I'm going to constrain them in the x direction. It's not going to change my results, but I do need to make sure that I'm constrained in all my directions. And you'll notice my my scarlet and gray, my Buckeyes. I have to work that in. The Ohio State University where I graduated from, and my Buckeyes. No accident there, but you can change these to whatever colors you want. Now I'm going to do my connectors. I move on to my next group, and my sheet metal shelf is welded at all 4 corners. So what I need to do, and let me just zoom in here so that I can show you that this is not really an edge connection. You can see it's more like a T connection there. Because I would get a nice weld bead in here. I overhang this surface out a little bit so that I can get a nice weld bead in there. So if I had an edge connection, what I would do, and I guess I should explain that because these are mid surfaces, my part was originally 1.5 millimeters thick. Well, now this mid surface is in the middle, so it's 0.75 away from the edge of the surface where the 3D surface used to be. And similarly, this one is 0.575 away from where, because it's a mid surface. So they're not touching anymore. So what if I had an edge connection? It's really more accurate. If I had a true edge connection where the 2 edges were line to line, then what I would do is I would extend this surface out and trim it back till they touched, and then I would use our unified body for that. But because this is really a T connection, I can use my edge connection and feel good about my results there. So all I have to do there is pick the edge that I want. And then my search distance, I just have to make sure that it is more than that thickness of the material. So I'm going to make it 2 millimeters there to cover the gap between them. And that's why Solid Edge makes it nice. I don't have to extend this out now because I have that edge connection. And there, it's as easy as that to do. And now I can come over and I'm going to turn off my loads and constraints here just so I can see this a little better. And I'm going to zoom in on this edge, and it's actually welded to the bracket. And I'm going to make my search distance 2, and then I'm going to attach that to the bracket, and I've got my connection there. And then I can spin around on this side and do my last edge connection over on this side. I'm sorry, my second to last edge connection. So I want to make sure my search distance is right, and then my edge connection is there. And then here is my last one. I was getting ahead of myself there. Now I just want to make sure I get the right edge, make my search distance, and I'm good with my edge connection there. So I've got all my edge connections done. Now what I want to do is I want to take a look at these ribs are connected to the bracket here with an edge connection as well. So what I want to do there, I'm going to turn off so I can select. I'm going to use my edge connection, but I'm just going to, and let me zoom in here, I'm just going to select these edges just like this so you can see how they're selected. I'm going to make sure I get my 2 millimeters there, and then I'm going to turn back on my bracket, and I've got my edge connection. So with sheet metal parts, you can really see how easy it is just to go around and make the connections that you want. Use another, and this will be my last edge connection. And then attach that to the surface of my bracket, and I'm good. So the last connections that I have to make, those are my edge connections. The last 2 connections I have to make are surface connections. I've got the table here, the shelf, connected to these ribs. And with the automatic connection, it's very easy to do. You just select the parts you want to connect, make sure your search distance is good, and then Solid Edge gives you some very nice feedback on what those connections are. So I've got my top rib, my middle rib, and my bottom rib, which is exactly what I want, and that looks good. And then my automatic connection, again, I want my shelf, let's make sure my search distance is good, connected to my brackets here. And then again, I get some nice feedback from Solid Edge on what we're actually connecting. You can see those 2 surfaces connected there, and that looks good. So now I've got all my connections done. So if I want to go through and at any time I can look in my Pathfinder here, or my Study Navigator here, I can see the geometry that I've selected, my 3 ribs, my 2 brackets, and my shelf. If I turn on my loading, I can see my loading. At any time if I want to go back in and check what I've done here, or I can turn on my label so that it says, and it's in millinewtons there. So I can look at my constraints. Anytime I want, I can check what I've done here in the Study Navigator. So that all looks good. I'm just going to turn that stuff back off there. And then I could go in and I could mesh. But in this case, what I'm going to do is I'm just going to go ahead and solve because I want to see what the default mesh gives me. And the reason that I want to do that is because I've made a bunch of assumptions here. I've made assumptions in how I've loaded the edges here, because in true life, really, I could not constrain an edge perfectly that exact point in the y direction. I could not do that in real life. So I'm making an assumption there by doing that. And because stress is equal to the force over the area, when I make the area extremely small by making it an edge or a point, the stress gets infinitesimally high. I mean, it gets extremely high, and we call that a singularity. And we know, because you can see it here, there's high stress around where I applied those constraints. And we know that this is not our area of concern, so we're not going to look at that. This is our area of concern. The principle says that the stress and the displacement in this area will be valid because, we just can't look at it in this area. I hope that makes sense. When you're thinking about what your area of concern is, you want to make sure that everything in your area of concern is included. So we're not going to say 51 is our maximum here. We're going to say the stress in this area is low enough, in the 5 to 10 range here, that it does not exceed our yield stress. And you'll see it's actually way under our yield stress. So I've made some assumptions around that. I've made some assumptions in my loading. I've made some assumptions in my material because I didn't go out and tensile test or compression test and get my exact material properties. I used handbook values. But all these assumptions up to this point are good because, like I said, we're very careful about our area of concern, and we know that steel properties are generally consistent, and the modulus is very consistent. So we're okay there up to this point. Now, my other thing is I've got to worry about my mesh because I'm using a mesh instead of the actual geometry, and I've got these little squares now trying to simulate or model curved surfaces. So the smaller mesh I have, the more accurate my mesh is. But that drives up my solve time. So what I need to do is figure out where it's valid. Where is that trade-off? So that's what I'm going to do. Let's take a look at displacement here. We got under a millimeter, so we've got 0.888 millimeters. So what I would do is I would just go in and let's close the simulation results. I would do a mesh sensitivity study. So I want to make sure, I'm going to just apply a surface size here, and just to be quick about it, it new with ST5 we actually give you what the default size is now. So I've got a 35 millimeter mesh size. I'm just going to have that, make it 15. And then I'm just going to select everything to save time here. And then accept that. And then I just simply can, that's what makes it beautiful about using simulation, is that I can just simply resolve. I don't have to do anything else. I apply my surface size, I'm done, I resolve, and I get my results. Because what I want is I want results that are independent of the mesh size. That's what I'm looking for. So I want to make my mesh small enough that I get good results, but not too small that my solve time is huge. So let's take a look at our displacement again, and you can see now it's 0.82. So what I would do is I'd rerun it again with a few more smaller mesh sizes. So let me just show you what that looks like here. So I've got my default mesh at 0.888 millimeters. I've got my surface size at 0.892. And then my 12 millimeter here, 935, 10 is 935, and I actually did 8 and 6, and they were 935 as well. So the difference now in getting smaller mesh is out here in the 4th, 5th, 6th decimal place, so that doesn't matter to me. So I can confidently say, with a surface size of 12, I'm getting very good results here. I'm getting results that don't change anymore when I minimize, when I make my mesh smaller, or my element size smaller. So now moving forward with this model, I can say I can use 12 millimeters and I've got good results. So this brings me to a good point here. Because our stress is so low and our displacement is so low, remember our requirements were that it had to be less than 6 and it's under a millimeter, and our stress is really far under our yield. That's my new engineering term, really far. So what I want to bring the point here is that a lot of people out there are making stuff now that they've been making for years, and they're like, well, it works, it's great. Well, that's great, but you could be saving a lot of money because you've over-designed it and you don't even know it. When you under-design it, you know it because it fails. When you over-design it, you don't know. It works, and it may work for years, but the problem is you may be spending more money, and your competitors may be coming in and undercutting you because they can make it for less because here, in this case, we could use a higher gauge sheet metal, which would make a thinner part, which would save us material costs. So you can not only use this for new parts, but also for parts you're already making to see if there's any room for improvement. Because it's so easy to just click that solve. Once you got a good model here, now I'm satisfied, I have a good model, I can click resolve and try different things moving forward. But before I do that, I need to consider vibration. Because this thing sits in a refrigerator, I've got it at about, the compressor's running, motor's running at about 50 hertz. So I need to make sure that my first mode or my natural frequency is not near 50 hertz, or I'm going to excite that natural frequency. So in order to do that, and you know why that is, because the maximum amplitude of displacement is going to be at that natural frequency. So you don't want your part displacing maximum. You want it displacing the minimum amount when it vibrates. So let's take a look at what we would do for a modal study. So we go in here to a new study, and we just take a modal analysis here, our frequency range. We just want to make sure that we're at least 4 times what our operating frequency is, which was 50 hertz. I'm just going to say 1,000 to make sure I cover that frequency. You can select how many modes you want, and then I want to make sure I get surface here. So that looks good, and then I would do the same thing, select my geometry. And now you'll notice that the loads are grayed out completely, and that's because with a modal study you use a unit force load. It won't let you, solid edge simulation won't let you make the mistake of trying to load it because the definition of a modal analysis uses a unit force load. Then I would move on to my user-defined constraints and set them up exactly as I did just a minute ago. I would use my edge connections exactly as I did and my auto connections exactly as I did, and then I would solve. But instead of wasting your time with that, let me just go into the modal results so that you can see them, because I don't want to solve and resolve. And notice I use that 12 millimeter because that's my good model. I know I have good results there. So when I look at my results here, I can see that my first mode is about 42 hertz. Well, that's a problem because I got 50 hertz as my excitation frequency. So now I've got something very close to that. It's going to excite that natural frequency. Well, when it does, let's use our Animate tool and we'll see how it moves. This is really critical that you understand not just what the natural frequency is, but what is that mode shape, because that's how we're going to fix this. We want to increase this natural frequency. Now, frequency is dependent on mass and stiffness. If you increase the stiffness, you're going to increase the natural frequency. Unfortunately, with increasing the stiffness, usually you're increasing the mass. When you increase the mass, you lower the natural frequency. So in this case, I've got this thing wagging in this direction here, meaning my stiffness in this direction is not high enough. If I want to make that natural frequency higher, I've got to increase the stiffness in this direction. So you might say, well, let me just take these ribs and move them and make them go this way instead of across like this. So if I made them go the long way, now I've got a problem. I would rerun this and I would see probably a very similar frequency, but it would be wagging in this direction because I would be missing the stiffness in this direction. So here is where your engineering comes into play. You've got to understand how this thing's moving so that you can figure out how to fix it. So I need to increase stiffness here without increasing mass too much. And the beauty here again is that I can play around and resolve it so fast that I can really hone in on a good design. Now again, if I wanted to, I could go in here and create a report if I wanted to, and this thing just amazes me. that this happens so fast, but and I didn't turn off my Animate Tool, so now I think it took a little longer than normal. But anyway, in one click of a button, I've got all my study property, my geometry, my material properties. I've got everything I need, including all my pictures, so that I don't have to do that myself. I used to spend a lot of time cutting and pasting. This is just beautiful. It looks way better than I would ever put together, too. So it tells you where the model is. It tells you everything that you've done to the model, all your connections, so you could recreate this if you had to, and it also gives you your pictures. And that's fantastic to show to your customers. What I did then is let me just close these results here, and I want to show you some of the designs that I went through. So I took a look at that. I needed to increase the stiffness, and what I did was I went through about 4 different designs, and what I came up with was a way to increase the stiffness without increasing the mass. And the way I did that is I had to find a way to constrain this without increasing the mass too much. So what I did is I added another bracket there, because now it's constrained. So now it's stiffer here because it's constrained here in the middle. And I didn't increase the mass too much, and I actually went to a 20 gauge sheet metal, which means my part is now considerably thinner. My parts are now considerably thinner than they were, so I'm saving in material costs. And if we take a look at this mode, you can see now that the mode is up at 100. So I was able to do that. And then I can see it's still that wagging direction, but now it's up at 100 because I've managed to increase the stiffness here by constraining it here. If I'd added another rib here, it would have increased the mass without increasing the stiffness enough. So I needed to constrain it here, and that's what I found through doing the study. So that's really how you get to a good design using this product. Okay. So now what I want to do is I'm just going to close out these models, and I'm going to move on to my thermal analysis. So have you guys ever been changing your brakes after you just got your brake pads? You went out, bought your brake pads, came home, tried to change your brakes, and felt how hot those rotors are. They get steaming hot. So I've got this 97 pickup truck. It's a Dodge. I love it. It's great. Now it does have some issues. The defrost doesn't work at all. But it's a great truck. I don't make a payment on it, and it keeps on running. Now, what I want to know is how hot are those rotors getting? So what I'm going to do is go to my thermal analysis. So here's what I want to know. How hot do these get when let's say my truck's sitting at the top of a hill, and it's 5,000 pounds, my Ram pickup, and it's a hill of a certain height. So it's got a potential energy sitting at the top of that hill. Now I'm going to come down that hill at a given speed, and I'm going to stay constant at that speed, pushing on the brakes. So I'm going to stay like, 60 miles an hour. Well, for me, it's more like 80, 90 miles an hour. Anyway, coming down the hill, I'm going to go the same speed and in a given time. So I can say this is a steady state problem because I'm staying at that constant speed, pushing on the brakes, and I want to know how hot these brakes get. So I use that potential energy, which is just the weight times the height of the hill, weight of my truck times the height of the hill, and I have to absorb 85% of that with my brakes. So because you got losses with friction and whatnot, 85% of that energy has to be absorbed by the brakes. I've got 4 brakes, so I divide that by 4. I got a spreadsheet, I calculate that out, I get about 2,400 watts. So this brake has to absorb 2,400 watts of energy, and I want to see how hot it's going to get. This brake cannot exceed 400 Celsius, and the thermal expansion can't exceed 3 millimeters because I've got a design envelope it's got to fit in. So I just want to turn off what I don't need. I'm going to stick with the hub that's in the middle here and the rotor. And I'm going to start a new study, and it's going to be linear static and heat transfer. I'm going to pick the tetrahedral element, solid element. I've got kind of a solid part here, and I want to generate all the results, not just the surface results. Then I can select my geometry. I just fence select. And now I can apply my loads. And you can see I've got new with SD5, I've got thermal loading, I've got a heat flux, a heat generation, convection, and radiation. Now I'm going to talk about all of these in detail when I get solving. It's going to take a minute to solve here, so I just want to use that time to discuss this. So I'm going to apply my 2400 watts. I've got a new total load option, so I can apply it to both surfaces. And 2400 watts. And then I want to make this a little bigger so you can see it. And there it is, 2400 watts heat flux, which is just the energy in. That's where the brake pads go on those surfaces. Now the other surfaces see airflow, so I'm going to put a convection on all those surfaces except for the surfaces where I have my heat flux. So I'm just going to select off of those. And then my film coefficient, which I'll talk about in a minute, I'm going to put at 50, and my ambient I'm going to leave at 20°C, which is about 68 degrees. And again, I'm going to make these a little bit bigger so we can see them. So that's what my problem looks like. All I have is the heat flux here, and then I have my convection on the rest of the surfaces. Now what I have to do is go to my constraints. So let me just turn off that loading here, and I'm going to fix where this is attached to the axle. And that looks good. And then I need my connection, so I'm just going to auto connect. And I get my feedback that I got two parts connected, which is what I wanted. And again, I can check over here my connectors, my constraints, my loads. I see my heat flux, my convection, and make sure everything's good. And then I can just go ahead and solve. Now, while this is solving, I want to talk to you about heat transfer. So heat transfer is just energy in transit due to a temperature difference. And there are three different types of heat transfer. You've got conduction, convection, and radiation. With conduction, let's say I have this surface and it's getting hot. What happens is the molecules that are on this surface are absorbing energy. Because they're absorbing energy, they start to move faster. When they move faster, they excite the molecules around them. And that's how heat is transferred. We call that diffusion. With conduction, the molecules get excited, they bump into the molecules next to them, they transfer some energy, those molecules bump into the ones next to them, and so on, all the way down to the other side of the surface. Now, with Fourier's law, we can say that the temperature on this surface minus the temperature on this surface is divided by the distance between those two surfaces for a one-dimensional problem, times a certain constant is equal to the heat flux. Now, that certain constant is called the conduction coefficient, and that's what you're going to need to enter when you do these studies. So it's one of the things you're going to need to enter. And you can find that it's a given value for any material. So you can use the internet, use whatever your sources are that you normally use to get material properties, and enter that conduction coefficient. Now with convection, let's say I've got this surface here that's heating up, and now I've got diffusion, so I've got the molecules here are bumping into the air molecules here, or whatever fluid this is. Let's say it's water, whatever. Well, we'll just say it's air. So they're bumping into the air molecules, exciting them, and you've got that transfer of energy. So those are heating up the air molecules with diffusion. Well, also those air molecules are going to start to rise because they're getting warmer and they're getting less dense. So you've also got this bulk fluid motion. So you've got two forms with convection. You've got the bulk fluid motion, which is called advection, and you also have the diffusion that we were talking about. So there's two forms of heat transfer with convection, two forms of energy transfer. So we can say with Newton's law of cooling that the temperature of this surface minus what they call T infinity, it's just the air way away from that surface, the temperature of the air way away from that surface, times a certain constant is equal to the heat flux. Well, that certain constant is called the convection coefficient. The convection coefficient is not as easy to just look up. It's dependent on this material but it's also dependent on whatever fluid you have, and it's also dependent on the geometry. So you're going to have to spend a little more time researching what convection coefficient you want to use. Now, there are cases where people out there, they'll do a computational fluid dynamics study to find out what the constant, the convection coefficient is for a certain situation. They publish that out there. So you can go out on the internet and find a good value and use that. So it's just a little harder to figure out. Now, the last form is radiation. So with radiation, you've all stood out there in the sun. It's just electromagnetic waves carrying photons, so you don't need a medium for them to transfer through. And you've got Stefan-Boltzmann's constant, which says that the surface to the fourth power times the Stefan-Boltzmann constant. That's the Stefan-Boltzmann equation. And then you multiply that by emissivity to get the heat flux. The emissivity of is another material property that you look at, and an ideal radiator is a value of 1. It radiates perfectly, it's a value of 1. So everything you're going to do is going to be below 1. So my stress values out in my area of concern here, again, we can't look at where we've constrained this. So that's, just to finish my thought, that's radiation. And you can look up emissivity and use that if you're going to consider radiation. So the results are back here. Stress is going to be high around my constraints. We know that. We ignore that. Out here, it's very low, as it should be, because of the fact that we've got it. We don't have the thermal growth constrained at all, really. So I want to take a look at what my temperature is, and you're going to see that it's about 392 degrees Celsius. So it's just under my my 400, which makes me a little bit uncomfortable because it's so close up against there. Now my stress is pretty low, but I still have got that temperature, you know, up there. Now let's look at my displacement. If I take a look at my displacement, I'm under 0.5 millimeter. So that's good. I've met my 3 millimeter requirement there very easily. But let's say I wanted to make some design changes because I'm kind of up close against that. So what I'm going to do here is I'm just going to make a couple changes to see if I can bring that temperature down. I'm going to move this back using my synchronous tools, which are very handy, to, let's say, 12 millimeters. And then I also want to angle it out a little bit as well. And I want to do that about 12 degrees as well. And that looks good. And then the last thing I want to do, I'm going to zoom around here to find my dimension. There it is. In New with ST5, I want to make this thicker. New with ST5, we can move both sides at the same time, selecting this middle button here, and you'll see how that keeps things symmetric. So I made that a little bit thicker. And really that's all I wanted to do with my changes. But you're going to see that now, since I have my simulation is so closely coupled with my finite element packet, or I'm sorry, my geometry engine and my finite element are so closely coupled. So Solid Edge is so closely related with simulation that I can just easily hit solve again and everything stays the same. So I can make changes as long as I don't change you know, something that has a constraint, or you know, something that's attached, or like if I remove a face where there's a constraint, it's going to show you one of these exclamations saying you need to fix that. But here it's saying my mesh is now changed because my geometry has changed. I need to remesh, and that my results need to be redone as well because the mesh has changed. So here I would just hit solve and resolve, but instead of doing that, I'm just going to show you what my results are so that we don't waste time. And you can see now that I've got about 372 degrees, so I've brought it down 20 degrees, and I'm a little bit under now my my design limit of 400 degrees, so I'm happy with that. Let me show you something we can do here with, we can select isometric contours so that we can see the bands of the different temperatures. And let's say I want to change how many levels I have there. So let's say I want to make it 24. I can make 24 levels so that you can see now in the color bar I have 24 different. And then I also, which is really helpful I think, I can do a dynamic where I can just scroll through and see the bands of color one at a time, or I can just type in, I want to see where it's 200 degrees. Boom, there, I can see 200 degrees. I think that's very helpful when you're trying to figure out what the temperatures are in the different areas. All right, so really that's what I wanted to show you with solid edge simulation. I want to make sure I drive home that you use this early in the design process, because I showed you how easy it is. You can rerun stuff. Once you get a good model, you can just hit solve after your changes are made and rerun it and see what the difference is, because you can easily use this tool to compare different models once you have a good model. I mean, that's a great use of solid edge simulation. And you can also reduce your physical prototypes, so you don't have to make all these things. You can just go ahead and run these models and see, narrow in on 2 or 3 that you like, or just one and make one. And then you want to carefully consider your simplifications. Like I said, you want to make sure that you have a specific area that you're targeting, and everything in that area, draw a box around it, and everything needs to be included. And then validate your results. Get a good model working, and then make your changes and compare. Thank you very much for your time today. If you have any questions, feel free to contact me. I had my contact information up at the front. Here it is right here. Here's my email address if you need to contact me. I'd be happy to answer any questions. Thanks again.